Okay, so now let's look at how the electrons get arranged in the orbitals. We've talked about looking at the periodic chart and assigning the quantum numbers and saying where any one electron goes. Now we want to start thinking about how they're arranged completely. In the electron configuration, we're talking now not about one electron's address, but rather about the distribution of the electrons in the orbitals and where they kind of hang out and how they go in. So we said that orbitals can be thought of as standing wave functions, and it describes the area in three-dimensional space where it's probable that we will find an electron. So these wave functions have mathematically well-defined shapes, and now we're going to think of that. And remember, within these shapes, we talked about this the other day, we have nodes, which are areas of no electron density or zero probability that we would have electrons there. So when we talk about the first orbital, that's the s orbital. And we talked about the s orbitals are in these first two columns, or the L is equal to 0 block for the subshell. And when we look at the s orbitals, we have one per n value. Every n value from equal or greater than or equal to 1, we have one s orbital. The s orbitals are spherical in shape, and we have increasing size with increasing n value. They increase in size with n value. So a 3s is bigger than a 2s. And this is where L is equal to 0. And when we represent an s orbital, we often just draw it like this. Well, not quite a circle. But this is what an s orbital looks like. So it is a sphere. Now, if you look at this and you see, oh yeah, now I'm upside down. This is not going to work. Okay, if you look at this, you see it in three-dimensional space. So this is the x-axis going across, the y-axis goes up and down, and then the z-axis. So this is at the origin in three-dimensional space. Inside that orbital, where the nucleus is, there is a node, an area of no electron density, because we don't have electrons in the nucleus. So at the origin, where the three metal rods go through there, that's where we have the node. Now, the p orbitals, we have 3 per n value, when n is greater than or equal to 2. So we look at this on the periodic chart. When we get over here on the right-hand side in these 6-column section, this starts at n is equal to 2, because remember, helium is not up here. Helium's over on the other side. So the p orbitals are described as being dumbbell or propeller shaped. Now, I have some models of these, and I'm not really happy with these models because of the paint job on them. And when you look at these kind of look more like dumbbells. So these are the p orbitals. And what I don't like about the paint job is when I look at this, I see two balls. I see a red ball and a yellow ball. And I don't think of that in my mind as one thing. And every semester when I pull these out, I think that I should come in at night and spray paint them so they're one color. So there are 3 p orbitals, and they are equal in energy, and they are oriented in three-dimensional space at 90 degrees to each other. So this is the px. It's on the x-axis as you're looking at it in the class. Here's the py. That is at 90 degrees to the x. And here is the z coming in 90 degrees. So these are oriented at 90 degrees to each other in three-dimensional space. And we could think of superimposing them on each other if I could. So it'd be kind of like this. And then the Z orbital would come in here, but I won't be able to get those together. So when we think about this in three-dimensional space, if we look at the X, Y, and Z axis going into the board, these are usually drawn more propeller looking and less dumbbell looking. So there's the PX, the PY is at 90 degrees, and the PZ is at 90 degrees there and going into the plane of the board and coming out of the plane of the board. So these orbitals are oriented 90 degrees to each other in three-dimensional space. And that is going to become more important later on when we start talking about molecular shapes. Because when we think of the orientation in three-dimensional space, that gives us an idea where the nuclei are. Now the d orbitals, there are 5 per n value. Once we get to the third energy level, where n is greater than or equal to 3. 4 of these are shaped the same, and 1 of them is different. When I look at these d orbitals, the first 4 that are all the same, I think of these kind of looking like 2 p orbitals overlapped on each other. And again, same issue with the paint job here, that this looks like a red one and a yellow one, and it's really 4 lobes of the same thing. Now, this particular one that I'm holding on the camera right now so that the people watching the video can see this, you'll notice that this is oriented in three-dimensional space on the X and the Z axis. The rest of them are oriented between the axes. So when you look at the rest of them, they're all in between the axes. So we look at these, and the names are not important for this class, but if we line them up correctly, we'll have some that are on the X and Y axis, some on the Y and Z, and one on the X and Z. They're all at 90 degrees to each other, and then this one goes in between. And the last p orbital that's different, it's kind of my favorite. This one's called the DZ squared. And again, the name's not important. I just think it's funny. But this one, to me, looks more like a p orbital wearing a life ring. You know, you put one of those little rings on and go jump around in the pool. Okay? So the crazy thing is this is shaped quite differently. It looks different. It's not the same as the others, but it is the same energy. So we have 5 d orbitals. Even though they're shaped differently, they are all equal energy. So 4 of these I think of as like 2 p's put together, and 1 I think of like a p with a lifesaver. But even with the different shapes and different orientations in three-dimensional space, they are all equal in energy. The f orbitals, we have 7 orbitals, and these start when n is greater than or equal to 4. And when you look at the periodic chart again, down here, when L is equal to 3, these are the f orbitals, and this starts when n is 4, when we're in the 6th period. And for these, I just say the shapes are more complicated, and for this class, we really aren't that interested in these. But 4 of them are shaped the same, and then 3 of them are different than that and the same as each other, and they're different in three-dimensional space. So if you look at these, I think these look like 2 d orbitals because you have 8 lobes, and then these are like the p orbitals with the double life ring, okay? So we have 4 that are shaped like this with 8 lobes. And then we have 3 that are shaped like this. And these have various orientations in three-dimensional space on the X, Y, and Z axes. And the shapes of these will not really be discussed in our bonding chapter because these don't come in to play in hybridization and bonding and molecular shape.